today the basic technical summary of what we just talked about. So back in Model 33, which, oh yeah, we're having some trouble now with this again, aren't we? Not too bad. Back in Model 33, back up. Oh, okay, great, thank you. Where we have the yi's given theta i's are independently normal theta I vi, where the vi's are known, and then theta I given alpha and beta and sigma squared theta are independently normal with the regression mean alpha plus beta xi minus x bar and sigma squared theta, and then we have to put priors on alpha, beta, and sigma or sigma squared theta. Now I want to talk about that. And so basically what I wanted to summarize was the research consensus is the following well-calibrated diffuse priors on alpha, beta, and sigma squared or sigma theta. Namely, alpha normal with mean 0 and huge variance. Beta ditto, normal with 0 and huge variance, which of course in both cases means tiny precision, e.g. 1.0 e minus 6, and sigma theta uniform from 0 to c, where c is chosen, c just large enough, right there, just large enough to avoid truncation of the likelihood function. That turns out to be your basic plan. Yes, please. Could I draw what? The plate diagram of this model. Sure. At least in principle. So he's asking about the graphical model that corresponds to this particular algebraic model. So let me remind you on this sheet what the algebraic model is again. So we have yi given theta I are independently normal theta I vi, where the vi's are regarded as known. Theta I given alpha, beta, and sigma theta, let's call it, are independently normal with means alpha plus beta xi minus x bar and variance sigma squared theta. And then alpha, beta, and sigma theta have some prior.
Does it matter if it's 3 more?
No, not really. We could put either one. So that's our model in algebraic format. And so now let's draw the plates. We're going to have dot, dot, dot out to the final one back here. Dot, dot, dot. And so now this is I running from 1 to n, going this way along the plates. And yi is a stochastic node in here. And the only thing I need to know to simulate yi is what, according to the algebraic model? Theta I. And theta I is also a stochastic node in this model. So I put theta I into that plate for I, and I write a causal arrow going from theta I to yi. I don't have to worry about the vi's because they're deterministic. I could put them out here as a deterministic vector, and I can also think of the yi's as as deterministic numbers because I'm going to condition on them. And I could drive the y's by the v's also, except there's nothing to learn there because the v's we're pretending that they're known. So if you know the theta i's and the v, you can simulate the y's. And then, according to the hierarchical model, what do we have to know to simulate the theta i's? Alpha, beta, and the variance. So they sit out here as stochastic nodes in the prior, alpha, beta, and sigma, let's call it sigma theta, And you also need to know the x vector as well. Actually, all you really need to know is xi, but we might as well have the whole x vector. But the x vector is deterministic, and so these things are all driving the thetas. And there's your graphical model, right? I think that's all there is to it. We have to put priors on alpha, beta, and sigma or sigma squared theta. X and V are known. Knowing these things here allows you to simulate the thetas. Knowing the thetas and the V's allows you to simulate the Y's. So there's your graphical model. Pardon? So there's your graphical model. Yes, what happens is, for calibration purposes, if you pick a value of C that's too large, what you'll find is that your so-called 95% intervals for alpha and beta, and for that matter for sigma theta, turn out to have actual coverage more like 97, 98, 99%. In other words, they get wider than necessary. So it's been found that if you pick a value of C that's just large enough to avoid truncation of the likelihood function, that will produce intervals, so-called 95% intervals, that actually include the truth about 95% of the time. So there's a danger in making C too small, because then you're actually chopping off the likelihood function, and you get those horrible pictures in the posterior where it gets truncated artificially. And there's a different kind of danger when you make C too big. It forces the intervals for everything you care about to be wider than they need to be to get good calibration. So this is, again, another Goldilocks and the three bears thing. Porridge too cold, porridge too hot, porridge too straight. When C gets too large, the posterior for sigma theta gets wider and wider, because especially, and I should say all of this is when, let's let I run from 1 up to capital I, the number of studies, and this part is particularly important when capital I is small. When capital I is big, it doesn't matter that much what you do with this prior. Particularly important when capital I is small. And the reason for that is that when capital I is small, the likelihood information about the between study variability is weak, because we don't have much information. Imagine having only 2 studies or only 3 studies. Then if you put down a uniform prior with a really big value of C, the likelihood function is going to say, well, it could actually be kind of far out there, couldn't it? And the result will be that your posterior for sigma theta will be a lot wider than it needs to be, and you'll end up with intervals both for it and for the other things that depend upon it that are wider than they need to be. That's the heuristic here. Yes?
Would this advantage of using uniform priors for all the parameters?
Say again? You could. The normal prior with mean 0 and huge variance behaves locally like a uniform prior from blah to blah, where left-hand blah and right-hand blah are again chosen not to truncate the likelihood function. But this is a nice way to approximate that in a way so you don't have to choose the left-hand blah and the right-hand blah. They come automatically from this.
Not really. But you still choose the spread.
Did you buy my point that if we put down uniform priors from minus C1 to plus C2, for example, for this thing here, if you have to fiddle with the C1 and the C2, you run the risk of truncating the posterior for each one. And then when you make them big enough so you don't truncate things, it turns out for the alpha and the beta that it doesn't matter if you make them bigger and bigger. That does not affect the inferences for everything else. Whereas for sigma, it does affect it quite a bit. That just turns out to work that way in the arithmetic of Bayes theorem. Okay. So, coming back to the PDF, we've now we've finished most of the story about the thetas. I've shown some stuff, and I'm now down around page 42, and the part that I want to show you for sure is a little table that I made on page. This is interesting also because on page 40, 6, we get to compare the mu values with the theta values. So you recall that each theta was like a normal draw with mean mu, and the result is then each y was like a normal draw with mean theta. So it's a sort of a double hierarchy. Y is varying randomly around theta, and theta is varying randomly around mu, and mu is driven by the alpha and the beta and the x value. And so if you look at these things, you see that the mu's and the thetas are not the same, and that's because what's happening is shrinkage toward the line that we talked about before. So I created a little summary of that here. In a manner parallel to the situation with that simpler model where we don't have any study level predictors, the posterior means of the underlying study effects theta I should be at least approximately related to the raw effect sizes y sub I and the mu sub I by a shrinkage equation like this. So the posterior expectation of y, a theta I given y, should behave something like 1 minus b hat for that particular study times yi plus b hat for that study times the posterior expectation for mu I given y. So this is like a little generalization of the shrinkage equation I showed you before. And the bi hats have the same behavior that they did before. And sigma hat squared is the posterior mean of sigma squared for the thetas. And so I wrote a little bit of code in R. I read in the posterior means for the mu's in as a vector called mu. I read in the raw data values in a vector called y, and I read in the posterior means for the theta vector and put it in a vector called theta. V was equal to 1 over tau, and I had previously defined tau as a vector of those quantities that we had before in the WinBugs data file. And then b hat becomes, like it says here, v over v plus the posterior mean of sigma squared theta, which turned out to be about 0.064, that quantity squared. And then theta dot approx, according to this shrinkage equation, should be 1 minus b hat times y plus b hat times mu. And I made a little table to see how well that describes things. So the real punchline here is that you want to look at the column called theta dot approx and compare it with the theta. And so this equation 11 back here, which is talking about, where is equation 11? 11 is the wrong number. That's interesting. So that's a mistake in the PDF, and if you're following along with a printed copy, you could fix that. It says down here, you can see that equation 11 is indeed a good approximation. That's equation 11 on page 48. Strike through the 11 and put in equation 34, right? That was, I don't know why I got that wrong. But now, basically, this is saying that an approximation to the posterior mean for theta should be calculable through this shrinkage equation. And look, the approximation is actually very good. So 0.0794, 0.081, that's pretty close, minus 0.034, minus 0.039. So basically, these things are tracking quite well. And also what comes out of it in a nice way is you get to see, again, those b hats. You get to see how much things are being shrunk toward the grand mean. Would you say the b hats are mostly big or small or in between? B hats, remember, they are of the form v over v plus a constant, and so they have to live between where and where. V is a positive and the sigma hat squared theta is positive, so they have to live between 0 and 1. Oh, no, I'm sorry, 0 and, I guess they have to live between 0 and infinity. Let's see, 0 and 1. So if sigma hat squared goes to 0, you get 1. And if sigma hat squared goes to infinity, you get 0. So they have to live between 0 and 1, which makes sense to use them as weights in a 1 minus b hat and b hat sense, right? Otherwise, the weights wouldn't make sense. And so if you look at the b hats, they're all pretty big, right? But remember what it means for the b hats to be big. That says the weighted average should put most of its weight on the grand mean. And what that says is that after adjusting for the number of weeks of prior contact, the covariate, there isn't much between study variability left. So no wonder the b hats are all big, because we're basically shrinking things 70, 80, 90% of the way back to the regression line. Actually, this all makes pretty good sense when you think about the numbers. So since sigma hat squared is small, in other words, since most but not quite all of the between study variation has been explained by the covariate x, the raw yi values get shrunken almost all the way toward the regression line. It is a bit of a mistake to pretend that the amount of between study variability left after adjusting for X is 0, which is what the MLEB approach does. But in fact, it doesn't provide that bad of an approximation here, as we saw when we did the modeling with the uniform 0C prior. Okay, now comes our most complicated hierarchical model to date. Yes, please.
So what happens, suppose that you ended up with a Bayesian result that was vastly different or significantly different than a frequentist. What would your reaction, what would you do?
My reaction would be, it's time to have a Pillsbury bake-off. So this is a situation where I get a really different answer from the Bayesian point of view than from the frequentist point of view. If they were the same, then they're both either right or wrong, and they live and die together. But if they're really different, then either both of them are wrong, or one of them is right and the other one is wrong. And I'd like to know which of those obtains. So what I would do is, like I've said before, create a simulation environment in which I knew the parameters and create multiple data sets from the basic model that I think is a good representation of what's going on, with known parameter values driving the data sets. Fire up the Bayesian machinery in one part of your code, fire up the frequency machinery in another part on the same data set. Build the intervals and just find out who does a better job of recovering truth. That's my standard answer to stuff like that. In other words, like I said before, I behave in a Bayesian way when formulating my inferences and predictions and decisions, but I'm quite happy to behave in a frequentist way when evaluating their calibration quality, by creating simulation environments where I know what the right answer is and see if the Bayesian story recovers known truth. And if it doesn't, I know there's either something wrong with the model or with the prior. And I go back and think again about my specification. Very powerful general tool. All right, so I began this whole course, actually, on page 2 of the entire course, back in week 1. I showed you the following, whoops, not page 2, but page 5. I showed you this data set here. So you may recall, or maybe not, it's been weeks, and there's been a whole lot of trees on the way to this new exploration of a piece of the forest. This guy called Dr. Hendriksen, who was a Danish physician, ran a randomized controlled trial in which he gathered together 572 elderly people, representative of the population of all non-institutionalized elderly people in Denmark, meaning that these are people who lived in their own homes or apartments, not living in a nursing home, not living in the hospital. And these people were randomized 287 to a control group that got standard health care, and the other 285 were randomized to a treatment group, and they got standard health care plus this intervention, IHGA, in-home geriatric assessment, which, as I described to you before, is a kind of preventive medicine in which each person's needs, health needs, also social needs, are assessed and acted upon individually. And they looked at a number of outcomes, but the one we're going to look at here is the number of hospitalizations each person experienced over the 2-year period in which the study unfolded. So a template of what the data set is going to look like at the time the experiment is designed is given here on this page 5 of lecture notes part 1. We're going to have a row in the table called control and another row called treatment. And we're going to keep track of how many people in the control group had no hospitalizations at all. We're going to call that number n sub c0. We're going to keep track of how many people in the control group had exactly 1 hospitalization in that 2-year period. We're going to call that n sub c1, and so on down to n sub ck, where k is the largest number of hospitalizations that anybody experienced in the whole data set, treatment or control. And then we have parallel counts n sub t0 up to n sub tk. And we don't know what those numbers are yet at the time the experiment's being designed, but we know this is going to be what my friends at the RAND Corporation, where I first learned about this data set, used to call, this is going to be one of the central table shells for writing the final analysis paper. It's a kind of a template or blank table for how the data is going to come out once someone actually runs the experiment. And it's really important, it's really helpful in designing an experiment. I learned this from people at RAND. When you're thinking of designing a study and you want to write about it afterwards, before you actually go and actually get the data, write out what you think the central analysis templates are going to look like. What do you want the final analysis? The paper's going to have 5 tables in it. What are they going to look like? And then bloody well make sure that the way you gather the data allows you to inform those tables in a valid way. So this is what the table shell is going to look like. We do happen to know the total number of people in the control group, N sub C, and all these numbers, N sub C0, N sub C1, up to N sub CK, they have to add up to N sub C, which is 287. Similarly, we know N sub T, 285. And as simple descriptive summaries of the control results, we can work out the mean number of hospitalizations per 2 years in the control group. Let's call that Y bar C. And similarly in the treatment group. And also let's get the standard deviations of those 2 things. So, okay. Now I'm prepared to unveil that actual data table to you now. So let's go back to part 4 of the lecture notes and get myself this page that we were just on. Here's how the data came out. Bottom of page 49 of part 4 of the PDF lecture notes. There ended up 138 people in the control group who had no hospitalizations at all versus 147 in the experimental group. So if you look just at the 0 column, who's winning? Treatment is winning, right? Because you want people to have no hospitalizations at all. Then in the 1 column, 77 for control, 83 for experimental. They're experimental winning again. And then when you start looking at the large numbers of hospitalizations, it's the control that's winning most of the time. So that all wraps up into means, and the control mean came out 0.944 hospitalizations per 2 years, and the experimental mean came out 0.768 hospitalizations on average per 2 years. That's a difference of 0.18 hospitalizations per 2 years, and it can also be expressed in relative terms as 0.768 minus 0.944 over 0.944, which turns out to represent a 19% reduction from the control level in the experimental group. Does that difference seem large to you in clinical terms? If you had something that you could do that would lower people's rate of hospitalization by 19%, does that sound like a worthwhile thing to do? Definitely. So when we talk about practical significance as a judgment different from statistical significance, would you guys say that this difference is practically significant? Is it large in practical terms? Very definitely. That's like asking the same thing I said before. Is it large in clinical terms? We in medicine, when trying to do this stuff, are often pretty happy if this number is 6%. So 19% is a home run, or at least a triple.
Cost of hospitalization? Dollars?
Now, that's a good question to ask. So far, this table here presents results of what might be described as a benefit-only analysis. And really what we ought to be doing is, from the Danish government's point of view, they have a question. They want to know, should they implement IHGA across the whole country? From their point of view, they're certainly interested in the benefit, which is right here in this table, at least as far as hospitalizations goes, but they're also interested in the costs and the cost-benefit trade-off. And in fact, your question is quite on point. 0.18 hospitalizations per 2 years, which is about 0.09 hospitalization per year, for example. If each hospitalization costs $25,000, then that's about $2,500 per person added up across the whole population of elderly Danish people who are non-institutionalized. That's going to be a lot of coin pretty fast. On the other hand, so the benefit comes out not only in these mean hospitalizations, but it also comes out in euro terms or dollars or whatever you want. I think kroner or something like that. Is that what the Danes at least used to use? But then the cost has to be factored in also, because IHGA is not free. You have to train nurses who are particularly, they have to give them special training, and they have to take time that they're paid for to go out to people's houses and do it. And I'm not going to show you the cost-benefit analysis results, but it turned out that this was good. This intervention was good both from a cost point of, or rather benefit point of view, and also from a cost-benefit point of view. And the Danish government did implement it on the basis of this experiment. Now, of course, when we do an experiment like this, we're not just interested in seeing what happened descriptively in the actual control group and in the actual treatment group that we have. We're interested in trying to generalize outward from this data to the larger universe of all the people who are similar to the people in the experiment in order to be able to make a judgment about what should be done for everybody in Denmark, not just the people in the experiment. Would you agree that, well, okay, I've already asked that question. Let me ask another one. So we've already answered the question in the affirmative. Does this difference seem large in practical terms? Next question. Does this difference seem large in statistical terms? And what people mean by that is the following. It's the answer to a devil's advocate sort of question. You imagine that you're in an argument with a devil's advocate, and the devil's advocate says, actually, let's agree to call mu sub t the population mean hospitalization rate in the control group, or rather mu sub c in the control group. Let's agree to call mu sub t the corresponding rate in the treatment group. And the devil's advocate says, do you know what mu sub c and mu sub t are? And we say, well, no. All we know is good guesses for them. Y bar t is a good guess for it is 0.768. Y bar c 0.944. I'm sorry. The y bar t 0.768 is a good guess for mu t. Y bar c, the control mean, is a good guess for mu sub c. But yes, devil's advocate person, I have to admit that I don't know what those things are. I only have good guesses for them. Devil's advocate person says, well, I think that in the population you're trying to generalize to, mu t and mu c are actually equal to each other. And we say, well, we don't think so. We got 0.768 and 0.944. Manifestly, those numbers are not equal. And the devil's advocate says, yes, but you only have a couple hundred people in each group. And these numbers are not the actual mu's. They're just guesses for the mu's. I think, the devil's advocate says, that the truth in the population is that mu t minus mu c is actually 0. And the only reason you got something that's non-zero is just unlucky random sampling. A combination of unlucky random sampling of people to get into your experiment and unlucky randomization. After all, says the devil's advocate, these people would have differed from each other at baseline on things like on things that are relevant to judging what is their basic propensity to become hospitalized. Some of them are older than others. Some of them are sicker than others. And so it might be that your randomization didn't do a good job of balancing all those potential confounders, right? So devil's advocate says, I think that the truth back in the population is actually that the difference is 0 and that therefore this relative thing you're interested in is also 0. And the only reason you got something that's non-zero is just unlucky random sampling and unlucky randomization. Do we have to admit that the devil's advocate's position